Hello everyone. In this session, we will discuss about types of power converter circuits and peripheral effects. Let us start with the types of power converter circuits. For the control of electric power or power conditioning, the conversion of electric power from one form to another is necessary, and the switching characteristics of the power devices permit these conversions. The static power converters perform these functions of power conversions. A converter may be considered as a switching matrix. Let us now see what is the categorization of power converter circuits. As you can see here, there are several types of power converter circuits, starting with diode rectifiers, also called as uncontrolled rectifiers. Then you have the line commutated converters or AC to DC converters, and these are commonly called as controlled rectifiers. Then we have the AC voltage or RMS voltage controllers, commonly called as AC to AC converters. Now, a further subcategorization of the AC voltage controllers is the CYCLO converters, which has a very small difference between that of the AC to AC converters, that the output of CYCLO converters will be lesser with respect to frequency than that of the regular AC voltage controllers. Then you have the choppers called as DC to DC converters, then the inverters, DC to AC converters, and finally static switches. Let us start by discussing the very first one, which is the diode rectifiers. A rectifier, as we know, is simply a power converter that converts AC to DC. However, depending upon the type of the device that is being employed for performing the power conversion, you can further categorize rectifiers into controlled rectifiers and uncontrolled rectifiers. Uncontrolled rectifiers are those in which the switching devices does not have a controlled turn on process, such as a simple diode. We have seen in the previous session, a diode is an uncontrolled turn on and uncontrolled turn off device, and the power converters, particularly AC to DC converters that employ diodes for power conversion, can be categorized under uncontrolled power converters. On the other hand, if I, instead of a diode, use a thyristor, which is a controlled turn on device, the AC to DC converter then will be called as controlled rectifier. Now let us see a simple example of a AC voltage, a simple AC to DC converter using uncontrolled device. You can see here we have used two diodes. You can probably understand that this is a single phase full wave uncontrolled rectifier circuit, because now we say uncontrolled because we are using diodes. The type of the input supply is AC and the output is DC. However, since we are not performing any rectification, the output is a pulsating DC. You can see the output V0 is pulsating. Now the operation is pretty simple. In the positive off cycle of the input AC supply, diode D1 conducts and a load voltage will appear across the load resistance R. In the negative off cycle of the supply, diode D2 conducts and a load resistance appears across the resistor R. What should be noted here is that the moment the input half cycle starts, the diode in an ideal scenario turns on at time t is equals to 0, and therefore the load voltage simply follows that of the input supply in an ideal condition. Practically there will be a voltage drop or a ohmic drop of 0.7 for a silicon diode, because that would be the threshold voltage of the diode D1. That is what is the waveforms depict here. In the positive off cycle, diode D1 conducts and output follows the input. In the negative off cycle, diode D2 conducts and once again output is following the input, but now the voltage is reversed. That is, all the negative voltages now become positive voltages. An absolute operation can be performed on the input supply. So this is about uncontrolled. The word uncontrolled is specifically for the type of the device, switching device that is used, which is our uncontrolled turn on turn off device, which is a diode. Now going to the controlled rectifiers, which is controlled turn on devices, we have taken an example of a thyristor. The same example here the circuit has changed only with respect to switches. Instead of diodes, now we have used thyristors. Now, thyristor is a controlled turn on but uncontrolled turn off device. However, since the type of the input supply is AC here, each of the thyristor will get a line commutated or natural commutation takes place. During the positive off cycle of the input supply, the thyristor is ready to conduct provided a gate voltage is provided across the gate to cathode terminals. Now, the control comes in the form that the analyst is allowed or the user is allowed to give the gate to cathode terminal within the time frame of 0 to pi in each off cycle respectively. Now, whenever you give the gate voltage, the thyristor will start triggered or it will start conducting from that instant. Here we have assumed that the gate pulse, which is not shown here, is provided at a value of alpha from 0. Okay, so the thyristor T1 will start conducting from alpha, and whenever the thyristor conducts, it becomes a closed loop, it becomes a closed switch, and the voltage appears across the load. So the shaded portion of the curve, what you can see here in the second waveform below, this shaded portion of the curve is what you get as an output. A similar approximation can be extended for negative off cycle. Once again, we have triggered the thyristor T2 at a value of pi plus alpha, and the thyristor T2 will cause a load voltage to appear across the resistor R from pi plus alpha, and it will continue till 2 pi. Now, what will happen to the thyristors at the end of each off cycle? Now, since the type of the input supply is AC, at the end of each off cycle, the diode will get naturally commutated, or called as line commutated, and therefore it will stop conducting exactly at pi. T1 stops at pi and T2 at 2 pi. So this operation continues. That's why we call it as controlled rectifiers. So the application of AC to DC converters can be found in speed control of DC motors in DC drives, HVDC transmission, and battery chargers. Now let us go to the second type of power converter circuits, which are AC to AC converters, also called as AC voltage controllers or AC regulators. AC voltage controllers convert a constant frequency fixed voltage AC supply into a variable AC voltage, but at the same frequency using line commutation. They are mainly used for speed control of AC motors, fans, and AC pumps. Let us look at a simple circuitry that converts AC to AC. Now here we have taken an example of a triac. Triac, as we know, is a bidirectional current carrying capability device. So it will conduct in both positive as well as negative off cycle of the input supply. The supply once again is AC here, and the output is also AC. It's an AC to AC converter. Now let us see what happens. In the positive off cycle of the input supply, the track is ready to conduct, but once again you can see there is a gate terminal here. So the track expects a gate trigger to be provided with respect to its cathode terminal in order to conduct. Now the terminals of the track usually are called as MT1 and MT2 and can be reversed. Right. So whenever you provide a gate trigger, let us say from a value of 0 between 0 to pi, the track will start conducting from that instant. Here once again we have triggered the track at an angle of alpha from 0. So the track when the positive off cycle conducts and a load voltage appears across the load resistance R from the instant at which the gate trigger is provided, which is at alpha. So the shaded portion of the curve is what you will get as the output during the positive off cycle. Now exactly at 0, since the voltage across the anode to cathode or the voltage across the two terminals of a track becomes 0, the track ceases to conduct, and in the beginning of the negative off cycle, the track is once again ready to conduct provided you give another gate pulse. But now this time the voltage will follow that of the input and it will not perform any rectification or any regulation here. But what it does is it will expect a gate pulse to be given across the gate terminal and only then will the track conduct. So it is pretty similar to that of the positive off cycle. Assume once again that we have provided a gate pulse at a value of pi plus alpha, and the track starts conducting from pi plus alpha and it continues to conduct till 2 pi, at which once again it ceases to conduct or it simply goes into off state. So in the next positive off cycle, you would require the track to be given a gate pulse in order to make it conduct in the positive off cycle. So this process is simply repeated. And you can see we have now converted an AC into AC. The frequency of operation of the input and output are exactly the same, no change in that. However, what differs is the average and RMS values of the input and output voltages. If you want to find out, you'll simply have to integrate the output voltage from alpha to pi instead of integrating from 0 to pi. For the input, now you'll have to change it from alpha to pi in order to obtain the RMS and average values. You have to perform this operation for one full cycle. Right. As I already have said, there is a subcategorization of AC controllers which is called as cyclo converters. Now, this is basically applied for applications which expect a little different frequency at the output as compared to that of the input. Now, they perform the same operation as that of a regular converter, except that the output voltage is at a lower frequency than that of the input voltage. That is the major difference between the AC to ACT converters and cycloconverters. So, the major application of cycloconverters comes in traction vehicles and gearless rotary kilns. Now, going to the next type of control converter, which is the chopper, also called as a DC to DC converter. Now, the name once again is pretty similar. You are converting a DC voltage into a DC voltage, but the output voltage differs with respect to the input voltage, once again with respect to the average value. They are employed they usually employ forced commutation techniques to turn off the thyristors that are used in the operation. Choppers are further classified into several types depending upon the direction of power flow and the type of commutation required. Based on the type of commutation, they are called as naturally commutated choppers and forced commutated choppers. They are widely used in speed control of motors from a DC supply, DC drives for suburban traction, and switching power supplies. Let us see a simple example of a DC to DC converter. Now, as you can see here, we have used a diode which is also called as a freewheeling diode, and this is very useful when the type of the load is inductive. Now, the type of the input supply is DC. We have used a transistor instead of a thyristor, so it would require continuous base voltage, and the transistor is more suitable because thyristor is an uncontrolled turn off device. So once it turns on, you would require an external circuitry to turn it off. So instead of that, we have used a transistor which will turn off the moment you remove the control voltage. Here the control voltage is the base to emitter voltage. Right. So the DC supply is not shown here. You can expect a constant horizontal line which is perfectly in parallel with respect to the x-axis. Now, the moment you provide a base voltage, and if the base voltage is greater than the VBE, which is a threshold voltage, let us say the transistor T1 turns on. And when the transistor turns on, you will see a load voltage appearing across the load here. Now, it is not shown what type of load it is. Either it can be an inductive load or a resistive load. Now, since you have been shown a freewheeling diode, you should expect the type of the load is inductive here. So, the input is continuous DC, but the output is pulsating DC. You can see. Now, this pulsating DC comes from the fact that it is the analyst who gives the base voltage to the transistor, and this base voltage is usually designed in a periodic way. Probably you can look at this. So between 0 to T1 you are providing a base pulse, and between T1 to capital T, which is a period of operation of the transistor, the output is 0. So whenever the base voltage is given to the transistor, output appears, otherwise the output doesn't appear. Now you can vary the width of the base pulse between 0 to T1 to obtain different values of average output voltage across the load. So now we have converted a continuous voltage DC to a pulsating DC. Fine. Then we come to the next type of power converter, which is called as an inverter. So inverters are used for converting DC power from a fixed voltage DC supply into an AC output voltage of variable frequency and fixed or variable output AC voltage. And since the type of the input voltage here is DC, these circuits will employ forced commutation techniques to turn off the thyristors used in the circuitry. And they usually find applications in industrial AC drives using induction and synchronous motors, uninterrupted power supplies, UPSs as we commonly call them as, used for computers and computer labs. We have a very simple example circuit depicting a DC to AC converter. Now the waveforms what you are looking at the left, the first two waveforms, they are the gate voltages applied to the MOSFETs that you can see, which are used in the DC to AC converter circuits. The type of the input supply is DC and the type of the output what you are looking at will be having a frequency, and therefore it is called as AC. Now what we do, since we have four transistors Q1, Q2, Q3 and Q4, we trigger two MOSFETs which are in the alternating arms of the bridge rectifier together in order to create a voltage across the load. For example, Q1 and Q2 are triggered together, Q3 and Q4 are triggered together. So correspondingly we have designed the gate voltage waveforms for the MOSFETs here. So here we have for VG1 and VG2, which is the gate voltage for MOSFET 1 and 2. So they vary between 0 to T by 2 and they are at a value of 1, and between T by 2 to capital T they are 0. Similarly, VG3 and VG4 are turned on when Q3 and Q4 are turned on when Q1 and Q2 are in an off state. So when I perform such an operation, so when Q1 and Q2 are turned on, you can see the left side of the load will be connected to the positive terminal of that supply and right side will be connected to the negative side of the supply. So you will get a positive voltage equal to that of the supply between 0 to T by 2. In an alternating manner, when Q3 and Q4 are turned on, the left side is connected to the negative of the supply and the right side is connected to the positive of the supply. Now the load voltage is reversed. It is anyhow with respect to amplitude it's equal to the supply, but now since the load is now connected in a reverse manner as to when Q1 and Q2 were on, the load voltage is assumed to be negative. So that's why you will get minus Vs. So this operation is repeated to obtain a, you can see here we are obtaining a rectangular output voltage which varies within one clock cycle. So you can vary the magnitude, sorry, not the magnitude, vary the width of these gate pulses to obtain different turn on turn off times and different average and RMS voltages across the load. So this is an example for an inverter. Finally, coming to the last type of power converter circuit, they are called as static switches. Now, since the power switches can be operated as static switches or contactors, the supply to these switches can either be AC or DC, and the switches themselves are called as AC static switches or DC switches respectively. Right. So that brings us to the end of the types of power converter circuits or also types of power electronic circuits. So we will now finally go into peripheral effects. Right, what is the need for peripheral effects and why is it important? Let us understand. Now, the operations of power converters are based mainly on the switching of power semiconductor devices, and as a result, the converters introduce current and voltage harmonics into the supply system and on the output of the converters. These can cause problems of distortion of the output voltage, harmonic generation into the supply system, and interference with the communication and signaling circuits. It is normally necessary to introduce filters on the input and output of a converter system to reduce the harmonic level to an acceptable magnitude. Such a particular system that provides or that subdues the peripheral effects is shown here. The control strategy for the power converters plays an important part on the harmonic generation and output waveform distortion and can be aimed to minimize or reduce these problems. The power converters can cause radio frequency interference due to the electromagnetic radiation, and the gating circuits may generate erroneous signals. This interference can be avoided by grounded shielding. Right, so that is about the peripheral effects, a very small discussion on that. Right, with that, we end the discussion on the different types of power converter circuits and peripheral effects. Thank you.